Guys, we are discussing in the topic Laplace transform, and up to the last lecture, I discussed various properties of the Laplace transform. First, I discussed what is the Laplace transform, what is the basic formula of Laplace transform. Then I told you if f of t is a function, then Laplace transform of f of t is equal to integral 0 to infinity e to power minus st ft dt. And I told you this is a definite integral depending upon the limits, and integration is with respect to t, and limits are constant after integration. Finally, we get a function of s. So we denote the Laplace transform of ft is equal to capital F of s. Right? This is the basic formula, and after that I discussed various formula of Laplace transform, like Laplace transform of 1 is 1 by s, Laplace transform of sin at equal to a upon s square plus 1 and so on. And then I discussed about the properties of the Laplace transform, in which three properties I discussed. One is linear property. A Laplace transform can be open, can be put inside the any linear combination, any expression, right? And we can calculate the separate functions, Laplace transform of separate functions one by one, and then I take the Laplace transform of open. You can first shifting property like that. If Laplace transform of such type of function e to power ft dt, then I will tell you this is directly by f of s minus a. And after that, we discussed in the last lecture change of scale property. If Laplace transform of f of at, then this is simply 1 upon a f of s upon a. And up to the last lecture, I discussed there will be also calculated the Laplace transform of some special type of the function, in which I took Laplace transform of ft. When ft is a periodic function with capital T, then I proved this formula 0 to capital T e to power minus st ft dt and upon 1 minus e to power minus s capital T. This is the formula. If function ft is periodic with period capital T, then we can directly calculate the Laplace transform of such type of function. Up to the periodic function I discussed up to the last lecture, and now today I am going to start other problems and other Laplace transform of other functions, in which if in this series the Laplace transform of some extraordinary functions, we can take Laplace transform of Bessel function first. Of Bessel function, right? In second semester, you studied Bessel function of order n in space solution special function. What is the Bessel function? I define. You know that this is r equal to 0 to infinity minus 1 to power r x by 2 to power n plus 2r upon factorial r gamma n plus r plus 1. This is the formula by which, and this is the n is the index or order of Bessel function. This is the main formula of Bessel function of order n, right? And by putting various values of n, we can obtain the various orders of Bessel function. Here, actually, we have to find the Bessel function of j naught x, Bessel function of order 0. So, if by this formula we put n equal to 0 and expand this, then we get the series form. This is 2 square plus x4 upon 2 square, 4 square minus x6, 2 square, 4 square, 6 square, and plus 1. If we put n equal to 0 and expand this series, is this summation sign, then we will get this infinite series. Now, we have to calculate the Bessel function of j naught x. By linearity property, we can separate them. Laplace transform of 1 by 2 square is constant. Laplace transform of x square, 1 upon 2 square, 4 square. Laplace transform of x4, 1 upon 2 square, 4 square, still Laplace transform of x to the power 6, and so on. Right? By linearity, we take this. And you know that Laplace transform of 1 is 1 by s. And also, we established the formula Laplace transform of t to power n or x to power n. This is gamma n plus 1 upon s to power n plus 1, and if n is integer, then gamma n plus 1 can be written as factorial n by gamma function's property, you know that. And so this is 1 by 2 square factorial, this is factorial 2 upon x s to power q plus 1 upon 2 square 4 square, that is factorial 4 and s to power 5 n minus 1, right? Now if you take 1 by s as a common, we get 2 is cancelled out, 1 by 2, 1 by s square. From here factorial 4 is open, 4 3 2, and it will be 1 into 3, and here 2 into 4, and 1 upon s, 1 s is common, 1 upon s4 and so on, right? This is the series. If you take this series and sum up this by the binomial theorem of any index, because in binomial theorem you know that 1 plus x to power minus n, this series. This can be written as 1 minus nx plus minus n minus 1 upon factorial 2 x square n plus 1, right? By this formula, it can be summed up as j naught x equal to 1 by s, this is 1 plus x means 1 upon s square, and n means minus half, right? And this is, so manipulate this, simply take that LCM, that is x square plus 1 minus half, so by power minus half it will be reciprocal, and so s upon under root s square plus 1, x is cancelled out, finally we get the 1 upon under root x square plus 1. This is the Laplace transform of j naught x, right? And this is the way by which you can find Laplace transform of Bessel function of any order. So please you try Bessel function of order 1, what is the Laplace transform of this, and so on, right? These are some extraordinary function for which you can calculate the Laplace transform by similar method, similar formula. Now, and again continue the various properties of the Laplace transform. In a chain of properties, now first we discuss the Laplace transform of derivative, right? Because as I told you, here we have to study three properties, three chapters of Laplace transform. One, main Laplace transform of various function, which is we are studying. Second, inverse Laplace transform, and thirdly, what is the application of Laplace transform? And in application, actually, we have to find the solution of ordinary differential equation by the using of the constant of Laplace transform as well as inverse Laplace transform. And so there it will be used. What is the Laplace transform derivative? If we take Laplace transform of ft is fs, then say that Laplace transform of f dash t, this is actually s fs minus f0, right? Please be careful about capital F and small f. I have already told you capital F is denoting Laplace transform and small f means original function, right? So first we have to prove that Laplace transform of first derivative, that is the first derivative of function, is this, right? Please first prove this, and then we can generalize and we can obtain the Laplace transform of any derivative of the function. If we take simply this f dash t, what is the first principle about it? First principle is pt e to power minus st f dash t dt. That is the simple basic formula, original function of Laplace transform. We only feed this f dash t. Now integrate this. We can integrate this by the part of integration by part. Take it as first function. This is the second function. Then by part, you know that first function integration of second function. So the f dash t integration is ft and upper limit, lower limit. Under sign of integration, differentiation of first function with respect to t e to the power minus t into minus s, and again integration of second function. And if we substitute upper limit, we get 0. If we substitute lower limit, e to power 0 1, and that is f0. Here minus a minus is outside, it is plus s 0 to s e to power minus st ft dt. If you see that this is, what is this? This is Laplace transform ft, that is capital Fs. So finally we get s capital Fs minus f0. That is your required result of the right hand side, right? That is the Laplace transform of the first derivative. Similarly, you can obtain for second derivative Laplace transform advantage. This is s square f of s minus s f0 minus f dash 0. Right? You can also establish this one in similar way. Okay, by first principle Laplace transform of f double dash t. That is 0 to infinity e to power minus st f double dash t dt. Again, by integration by part, we take it as first function and second function. Then first function integration of second function to integral of f double dash t is f dash t, and limits and under sign of integration, differentiation of first function, integration of second function. Here again substitute upper limit, that is 0, lower limit minus f dash 0. Take minus s as a common, that is plus s, and again integrating this, taking as first function, second function, and by integrating part e to power first function, integration of this, limits, differentiation of a function again, that is e to power minus st minus s, and integration of second function ft. Right, this is minus f dash 0 s in bracket. After substituting upper limit, it is 0. Lower limit, this is f0. Take minus s is outside s, and this is simply Laplace transform of ft, that is fs. Finally, we get this, right? This is the Laplace transform of second derivative. Similarly, you can obtain Laplace transform of third derivative. What is it? That is s cube f of s minus s square f0 s f dash 0 and minus f double dash. Right? This is the Laplace transform of third derivative. And in similar way, if we generalize this result, then we can obtain the Laplace transform of any derivative as Laplace transform of any derivative of this. This will be s to power n f of s to power n minus 1 f0 s of n minus 2 f dash 0, and final so on last minus f of n minus 1 0. This is your main result, this is your general result for the nth derivative, by which we can obtain any result, and that is the final result of the Laplace transform of derivative, right? And in differential equation, where we have to use the Laplace transform to solve the differential equation, we use these results, because you know that in differential equation we take ft y equal to ft, and y1 means dy dt of ft, and so on. Y2 means dt by dt. So by this formula we have to use the result this. Y1 means f dash t, and you have fs minus f0. Let me write this one. These results will be used to solve the ordinary differential equation. That is the first result, Laplace transform of derivative. Now, second, next one. Laplace transform of integral. Right? Laplace transform of integral. What is the Laplace transform of integral? If Laplace transform of ft is equal to fs, then Laplace transform of integral 0 to t fu du is equal to fs upon s. Right? That is the Laplace transform of integral, right? Laplace transform of integral. Right, proof now. First, again, we verify this first thing. If we let us take integral 0 to t f of u du is phi of t. Then from here, phi 0 is 0, number 1, and number 2, phi dash t equal to ft, right? These two results will be given. Ft is just an arbitrary function. So we take here Laplace transform of phi dash t. That is the Laplace transform derivative. Then we use the previous formula. What is that? This is S Laplace transform of phi t minus phi of 0. Then this is phi dash t is ft, Laplace transform of ft. This is S. Laplace transform of phi t means Laplace transform of 0 to t f u du, and phi 0 is 0. So from here we get Laplace transform of 0 to t f of u du is equal to, and you know that this is denoted by fs upon s, and that is your result. That is your formula which you have to prove. That is the Laplace transform of integral, right? This is the second formula, which can be used directly whenever we have to find the Laplace transform of integral. Okay, now next formula. Laplace transform of function of type t and ft. If some power of t is multiplied into the original function, then what is the Laplace transform? For that, if Laplace transform of ft is equal to fs, then Laplace transform of t to power n ft, if you calculate this, this will be minus 1 to power n, and a derivative of this fs with respect to s. This is the form, right? That is, if any power of n is multiplied this by this, you can obtain by putting n equal to 1, Laplace transform of t ft, n equal to 2, Laplace transform of t square ft, and so on. That is directly by this formula. If you know the Laplace transform of original function fs, so differentiating one by one, first order, second order, and so on, then you can obtain. First of all, we have to prove this. For n equal to 1, actually, we have to prove that Laplace transform of t ft, that is minus 1 d by ds of fs. Right. Very simply, we can prove this by original formula, as we know that Laplace transform of ft is 0 to infinity e to power minus st ft dt is equal to capital Fs. Right. This is the original formula. This is the first principle. So simply differentiate this. Differentiating it with respect to s on both sides, we get, right? This is d by ds of integral 0 to dt e to power minus st ft dt. Right hand side is d by ds of fs, right? And in left hand side, actually, you are differentiating integral. So there is a method, there is a Laplace rule. There is a Laplace rule. What is the Laplace rule? If you are differentiating definite integral with respect to another parameter, because integration here, integration is with respect to t, and you have to differentiate it with respect to s. So you can take process of differentiation inside the integral, but your nature of derivative will be changed. Here, its nature will be partial, because here it is an ordinative, but when you take it inside the calculation, inside the sign of integration, then it becomes like that, then it becomes partial derivative with respect to s. For partial derivative, so only function of s is e to the power minus st, ft is that thing, and right hand side is similar d by ds. This is the Leibniz rule. So we are using here Leibniz rule. And by this, we get 0 to infinity partial derivative of e to the power minus st is e to the power minus t, because integration is with respect to s, differentiation is with respect to s. So e to the power minus st is e to the power minus st, and then derivative of minus st is minus t, and d by ds of fs. Now, if you calculate this, then you will get your required result. Here we take minus, take outside the integral, infinity e to the power minus st, t ft dt is equal to d by ds of fs. Right? You transfer the minus sign on right hand side and see this. What is this? Actually, by first this by basic rule, 0 to infinity e to the power minus st t into ft, and this is the original function. So it is the Laplace transform of t ft, and take minus sign this side. So this is minus 1 to the power 1 d by ds of s. Now you have proved the result for t equal to 1, right? This is the Laplace transform of t into ft. In similar way, you can similarly we can obtain Laplace transform of t square ft is minus 1 square, second derivative of fs, right, and so on up to the nth derivative. Laplace transform of t to the power n ft equal to minus 1 to the power n nth derivative of fs ds, right? Like that. So these are first today I discussed these three results, and these are naturally some standard result, and you can use directly whenever you have to find the Laplace transform of such type of the function. Before going to the next topics, first we take some numerical example by which you understand what are the basic process to solve the given problem by using such results. So I am taking here first numerical example, some by which you understand better, and then continue this. If we take, find Laplace transforms of the following. Number 1, Laplace transform of t cos 2t. Number 2, t2 e to power minus 3t. Number 3, that is t e to power minus t sine 3t. Number 4, 0 to t e to power minus t cos t dt. Right? Actually, if we take these examples, and then you will understand better the application of such formula, such rules. Right? Now, take the solutions. If we take first, we have to calculate Laplace transform of t sine 2t. So here original function is ft. So first of all, you have to find the Laplace transform of ft means cos 2t, and this is the standard formula. I have already proved this in first lecture. This is s upon s square plus 2 square, means s upon s square plus 4, simply. So, and now it is time of t ft. Just I put this formula, minus 1 to the power 1 d by ds of fs. This is the formula. So Laplace transform of t cos 2t means minus 1 and d by ds, and this is your fs. So Fs means s upon s square plus 4. Simply differentiate this by ratio formula, by ratio method. That is 1. That is, you know that s square 4 whole square. That is s square 4, and differentiation of s is 1 minus s. That is differentiation of s square plus 4 is 2s. If we cancel out and take minus sign inside, then s square minus 4 s square plus 4 whole square, right? Because 2s square minus s square and take minus multiplied, then it becomes plus, and this becomes. This is your final answer. This is the Laplace transform of t equals to t, right? So first, what is this? And in similar way, you can solve this. Again, this is original function ft, and you know that ft Laplace transform e to the power 3 is 1 upon s plus 3. Similarly, you can this, because you know that original function is this, right? And we know that this is ft, and Laplace transform for that, we know that this is actually sin 3t. So we have 3 upon s plus 1 square plus 9. This is, so t times 1 time to differentiate this, you can obtain this, right? Here ft is this, you can obtain here. And now fourth case, I am taking fourth case. This is also depending upon the rule of Laplace transform of integral. That is, we have to find the fourth case. We have to find the Laplace transform of 0 to t e to the power minus t into cos t dt, right? This is, and we have the formula 0 to t fu or ft, you can say. This one I told you formula is, this is fs upon s, right? Means we have to actually, firstly we have to find the capital Fs. Capital Fs means Laplace transform of original function. So here if we see that ft is this, if we compare this, we have ft is this. It means here ft is e to the power minus t cos t. First, you find the capital Fs. Capital Fs means Laplace transform of ft, means Laplace transform of e to the power minus t cos t. And you know that Laplace transform of cos t is s upon s square plus 1 square, right? And by first shifting theorem, e minus t is multiplied. So only you have to replace s by s plus 1. So it becomes s plus 1 upon s plus 1 square plus 1 square. That is s plus 1 upon, if you open this whole square, s square plus 2s, and 1 is 2. Right? This is Fs. So by the formula, Laplace transform of 0 to t e to the power minus t cos t dt is Fs upon s. That is s plus 1 upon s times s square plus s2. Right? This is the Laplace transform of this function. This is the Laplace transform of integral. Actually, these formulae can be used directly, but first you have to find the capital Fs. Capital Fs means Laplace transform of original function. So first of all, whenever any sum, you have to check what is the ft. You have to find what is the actual function. Here you see that we compare this by this. So we get ft is equal to this. So first we have to calculate the Laplace transform ft, and that is your capital F of s. And that is also function to function. There is a chain of function e to the power minus t into cos t. Originally function cos t. Cos t, Laplace transform cos t, you know that s upon s square plus 1. And by first shifting theorem, e to the power minus t is multiplied. So a equal to minus 1. So only you have to replace in this function s by s plus 1. So we get this one, and this is our Fs. And by the formula of Laplace transform of integral, just I prove this. This is capital Fs upon s. So this, right? By using these results, you use these numericals, you solve these numericals, and today only I am taking these, and next lecture I will continue with other properties, with other means. Now we have also some interesting formula like Laplace transform of ft upon t, because there is no any formula. We have discussed Laplace transform of ft upon t. If t is divided, then what is the Laplace transform? First we discuss this thing, and then also there are some interesting other functions. Let's say Laplace transform of unit step function. There is a defined unit step function. Then what is the Laplace transform of unit step function? And there is also defined a function that is unit impulse function, which is also known as direct delta function. So what is the Laplace transform of direct delta function? and also some other properties and some interesting type of the sums we discussed this, and also there is using Laplace transform, there are some definite integral, and those definite integral can be evaluated, can be calculated by the help of Laplace transform. Okay, thank you.